China didn't just build bigger, it built what the rest of the world said couldn't be built. These are the megaprojects that permanently rewrote the rules of engineering. Structures so massive, so technically complex, and so audaciously conceived that they didn't just push boundaries, they erased them. China's high-speed rail network alone covers over 26,000 miles of track. That's enough to circle the entire Earth more than once. You heard that right. One country's train network, wrapping around the whole planet. And the rail network is just one item on a list that will genuinely change how you think about what human beings are capable of building. What you are about to hear isn't a collection of impressive statistics. It is the story of how one nation decided that impossible was just an engineering problem waiting to be solved. Three Gorges Dam. Picture a wall of concrete stretching 1 mile and 400 feet across the Yangtze River, rising 607 feet into the air, taller than a 60-story skyscraper, holding back a reservoir so massive it stretches 370 miles upstream. That is the Three Gorges Dam. And before a single foundation was poured, engineers faced a problem that had never been solved at this scale before. How do you build the largest dam in human history across one of the most powerful rivers on the planet, without the river destroying your construction site while you're building it? The answer was a construction sequence so precisely engineered it took over a decade of planning before ground ever broke. Workers first diverted the entire Yangtze River through a bypass channel, redirecting one of the world's great waterways on purpose, like rerouting a highway just to get access to the riverbed. Then they poured concrete, not occasionally, continuously. At peak construction, workers were pouring over 22,000 cubic yards of concrete every single day for years. The total concrete used in the dam structure could fill the Empire State Building more than 30 times over. But this is where the scale stops feeling like a construction project and starts feeling like something else entirely. The reservoir created behind the dam is so incomprehensibly large, holding over 1.4 trillion cubic feet of water, that the redistribution of that mass actually increased the Earth's rotational inertia. Scientists confirmed it. The planet's rotation slowed by a measurable amount. A dam built by human hands subtly altered the speed at which the Earth spins. The engineering achievement here isn't just the size. It's the precision required to manage water pressure, seismic load, and structural integrity at a scale that had never been attempted. Every single calculation had a consequence that could not be undone. China didn't just build a dam, it reshaped a river, displaced over 1 million people, and left a permanent mark on the planet itself. Beijing Daxing International Airport. You are standing underneath a roof that covers 1.7 million square feet, uninterrupted, column-free, flowing in every direction like something that grew rather than something that was built. Beijing Daxing International Airport doesn't look like an airport. It looks like a creature. From above, it spreads across the landscape in the shape of a starfish, with 6 curving fingers radiating outward from a single central hub. And that shape isn't aesthetic. It is pure engineering logic. The design challenge was this: move 100 million passengers per year through a single terminal without creating the bottlenecks, dead zones, and congestion that cripple every major hub airport on Earth. The solution was to ensure that no passenger ever walks more than 300 feet from the central hub to any gate in the building. In an airport this size, that is an almost incomprehensible geometric constraint to satisfy. The starfish layout solved it. But the construction timeline is where this project becomes something genuinely staggering. China broke ground in 2014 and opened the airport for full operations in 2019. 4 years to build one of the largest and most complex airport terminals ever constructed. For context, the expansion of London's Heathrow Airport, a project a fraction of this scale, has been in planning and political debate for over 2 decades without a single new runway being built. Then comes the engineering detail that most people never hear. The roof structure required over 52,000 steel structural members, each one custom fabricated to a unique specification, because no 2 sections of that curving, flowing canopy are identical. Every single joint was engineered individually. The roof essentially has no repeated components. It is one continuous, custom-designed structure that covers an area larger than 80 football fields. China didn't just build a fast airport. It built the most spatially efficient mega-terminal ever designed and delivered it in a time frame that made every other nation's infrastructure program look paralyzed. But building in the sky is one thing. What China engineered across open ocean is in a completely different category of impossible. Kong-Zhuhai-Macau Bridge. Imagine being asked to build a road across 34 miles of open sea through one of the world's busiest shipping lanes, across an active seismic zone, through waters that produce some of the most powerful typhoons on the planet, and do it without disrupting a single flight path from Hong Kong International Airport directly overhead. Every one of those constraints is real. Every one of them existed simultaneously. And China built it anyway. The Kong-Zhuhai-Macau Bridge is the longest sea crossing ever constructed. The total crossing stretches 55 miles when approach roads and connections are included. The main bridge section alone runs over 17 miles across open water, supported by towers rising over 200 feet above the sea surface. But the bridge cannot be a bridge for its entire length, because Hong Kong's airport sits directly in the flight path. So engineers designed a solution that had never been executed at this scale before. The bridge dives underwater. At the point where aircraft approach paths make surface structures impossible, the crossing transitions into a 6.7-mile underwater tunnel. To make that transition work, engineers constructed 2 artificial islands in the middle of the ocean, each one roughly the size of 6 football fields, to serve as the entry and exit portals for the tunnel. Those islands didn't exist before construction began. They were built from nothing, in open water, to connect a bridge to a tunnel in the middle of the sea. The tunnel sections themselves were prefabricated on shore as 33 individual concrete tube segments, each one weighing over 75,000 tons, then floated out to sea and sunk to the ocean floor with millimeter-level precision in moving water, with active shipping traffic above. Then comes the part that redefines what this project actually represents. The entire crossing was engineered to withstand a magnitude 8 earthquake, super typhoon force winds, and a direct collision from a 300,000-ton cargo vessel, simultaneously, if necessary. China didn't just cross the sea, it went through it. Duge Bridge. You are standing on a deck, suspended 1,850 feet above the bottom of a gorge. The clouds are not above you, they are beside you, sometimes below you. The Duge Bridge in southwestern China is the highest bridge on Earth, and the engineering challenge wasn't just building something tall. It was building something structurally perfect in a location that seemed specifically designed to make construction impossible. The Nizhu River Gorge, where the bridge crosses, is so deep, so narrow, and so geologically unstable that engineers couldn't simply crane materials down from above or haul them up from below. The valley walls are near vertical. The riverbed is completely inaccessible by road, so construction teams used a solution that sounds more like a military operation than a building project. They strung a temporary cable system across the gorge and used it to fly construction materials horizontally through the air between the 2 canyon walls, thousands of feet above the river. But this is where the tension in this project becomes visceral. The bridge's 2 main towers had to be anchored into canyon walls composed of fractured, unstable rock that geologists had serious concerns about. Engineers drove anchor cables hundreds of feet deep into the cliff face, essentially stitching the towers into the mountain itself to create foundations strong enough to hold a structure of this weight at this height under wind loads that fluctuate violently through a narrow gorge. The main span stretches 1,390 feet between towers. The entire deck weighs over 40,000 tons, suspended by cables under tension so extreme that the engineering tolerances had virtually no margin for error. One miscalculation in cable tension at this height, with this span, above this drop, the consequences would have been catastrophic and irreversible. China completed it anyway, on schedule, to specification. The Duge Bridge didn't just set a world record for height. It proved that no terrain on Earth is too extreme to cross. But building over impossible terrain is one challenge. What China engineered across an entire continent is on a scale no single structure can match. South-North Water Diversion Project. There is a point where an engineering project stops being a structure and becomes a geographical intervention. The South-North Water Diversion Project crossed that line before construction even began. This is not a dam, a bridge, or a tunnel. This is the deliberate, permanent rerouting of China's entire freshwater geography, moving water from the rain-soaked river systems of southern China to the arid, drought-stressed north across nearly 3,000 miles of terrain, through one of the most complex hydraulic engineering systems ever conceived. China's north holds 40% of its population, but only 8% of its freshwater. That imbalance isn't manageable at scale through conservation alone. It requires physically moving water across the country. So engineers designed 3 separate transfer routes: eastern, central, and western. Each one a complete engineering project in its own right, involving hundreds of tunnels, aqueducts, pumping stations, reservoirs, and river crossings built across mountains, plains, and earthquake zones simultaneously. The central route alone required engineers to solve a problem that had no precedent. The water needed to flow north, but the terrain rises as it moves away from the source. To cross the Yellow River, which sits at a higher elevation than the canal at that point, engineers built a pressurized underwater siphon tunnel that carries billions of gallons of water beneath one of China's greatest rivers, flowing uphill through hydraulic pressure alone, without a single pump at the crossing point. Then comes the scale that makes everything else feel small. The project moves over 10 trillion gallons of water annually across the Chinese landmass. The total excavation involved in constructing the canal network is estimated to exceed the total earth moved during the construction of the Panama Canal by a factor of several times over. China didn't redirect a river. It redirected its entire relationship with water. And if reshaping a continent's hydrology sounds like the most ambitious thing a nation could attempt, what China built reaching into the sky above Shanghai will make you reconsider that entirely. Shanghai Tower. You are looking at a building that twists, not metaphorically, literally. The Shanghai Tower rotates 120 degrees from its base to its crown, spiraling upward 1,632 feet into a skyline already crowded with super-tall structures. At 128 floors, it is the second tallest building on Earth. But the height is not the engineering story. The twist is, Shanghai sits in a typhoon corridor. Wind loads on a building this tall are not an inconvenience. They are an existential structural threat. A conventional rectangular tower of this height in this location would require so much structural steel to resist lateral wind force that the building would become financially and physically impractical. So engineers at Gensler solved the problem by making the building fight the wind with its own geometry. The tapering, rotating profile reduces wind load on the structure by 24% compared to a conventional tower of identical height. The building essentially deflects the wind around itself, shedding turbulence rather than absorbing it. That single geometric decision saved over 10,000 tons of structural steel, enough steel to build another significant skyscraper entirely. But this is where the construction challenge becomes something extraordinary. Because you cannot build a twisting super-tall structure using conventional vertical construction sequencing. Every floor is rotated slightly relative to the one below it. Every structural connection, every curtain wall panel, every mechanical system had to be designed and installed accounting for a geometry that never repeats itself from one floor to the next. The building has 128 floors, and almost no two are structurally identical. Then comes the detail that lands hardest. Inside the tower's upper floors, a 1,000-ton pendulum damper swings in response to wind movement, counteracting the building's sway in real time. The tower doesn't just resist the wind, it responds to it, dynamically, continuously, like a living system maintaining its own balance. China didn't just build tall, it built smart enough to survive. Vast radio telescope. You are standing inside a valley in the karst mountains of Guizhou province, looking down into a bowl so perfectly shaped by nature that Chinese engineers chose it specifically because the Earth itself had already done half the work. The 500-meter aperture spherical telescope FAST, is the largest single-dish radio telescope ever built. And the engineering required to construct it pushed the boundaries of precision manufacturing into territory that had never been explored before. The dish spans 500 meters across, roughly the size of 30 football fields laid side by side. It is made of 4,450 individual triangular aluminum panels, each one independently adjustable, controlled by a computer system that reshapes the entire dish surface in real time to focus on different points in the sky. The panels don't sit in a fixed position. They move constantly, precisely, by fractions of an inch, forming and reforming the focal point of the telescope as it tracks signals across the universe. But the construction challenge that nearly broke the project was this: how do you fabricate and install 4,450 unique panels, each requiring sub-millimeter accuracy, across a 500-meter curved surface in a remote mountain valley with no flat ground, no existing infrastructure, and no road access large enough to bring in conventional construction equipment? China built the roads first. Then it built the equipment capable of working in those conditions. Then it built the telescope. Then comes the payoff that puts everything in perspective. FAST is sensitive enough to detect a radar signal equivalent to a mobile phone transmission from the surface of the moon. It can hear radio waves that have been traveling toward Earth for billions of years. China built an instrument so precise that it can listen to the edge of the observable universe, and it built it inside a mountain. But pointing at the universe is one achievement. Harnessing the raw power of the planet's most violent ocean is something else entirely. Changhua Offshore Wind Farm. You are standing on the deck of a construction vessel in the Taiwan Strait, one of the most typhoon-prone, current-driven, geologically complex stretches of open ocean on the planet. And you are about to drive a steel foundation into the seabed in water depths reaching over 100 feet, in conditions that have historically made offshore construction in this region borderline suicidal. This is where China built the Changhua offshore wind farm, and the engineering required to do it rewrote the rulebook for offshore construction in extreme environments. The Taiwan Strait produces wind speeds that make it one of the most resource-rich locations for wind energy on Earth. It also produces typhoons powerful enough to destroy conventional offshore infrastructure. Every single foundation design, every turbine tower specification, every submarine cable routing decision had to account for both realities simultaneously. Maximize energy capture from extreme winds while surviving the most destructive weather systems the Pacific generates. Engineers designed monopile foundations driven over 100 feet into the seabed, some of the deepest offshore wind foundations ever installed, to anchor turbines against the lateral forces generated by typhoon-strength winds and the powerful tidal currents that characterize the strait. The installation vessels themselves had to be specifically engineered for these conditions, with dynamic positioning systems capable of holding precise location and currents that would push a conventional vessel completely off station. But this is where the project reveals its deeper engineering ambition. The turbines installed at Changhua are among the most powerful offshore wind turbines ever deployed, each one capable of generating sufficient electricity to power over 10,000 homes annually. The total farm output feeds directly into Taiwan's grid through submarine cable systems buried deep enough in the seabed to survive the same typhoon forces the turbines above are designed to withstand. China didn't just build a wind farm in a dangerous ocean. It turned the most hostile stretch of water in Asia into a power station. But generating power from a violent ocean is remarkable. What China built by creating entirely new land from the seafloor beneath it belongs in a different category of engineering ambition altogether. Hong Kong International Airport Artificial Island. There is a version of engineering where you work with the land you have, and then there is what China did for Hong Kong International Airport where there was no land, so they built some. The entire airport sits on an artificial island reclaimed from the shallow coastal waters off Lantau Island. Every runway, every terminal, every taxiway exists on ground that was manufactured from scratch, dredged up from the sea floor, and engineered into stable, load-bearing land, capable of supporting one of the busiest aviation hubs on Earth. The reclamation moved over 350 million cubic yards of rock, sand, and marine sediment to create an island covering nearly 3,000 acres. But the volume of material wasn't the hardest part. reclaimed land doesn't behave like natural ground. It compresses, settles, and shifts under load in ways that crack foundations and distort runways. Engineers spent years on ground improvement alone, driving sand drains deep into the reclaimed material to accelerate settlement and installing island-wide monitoring systems to track every millimeter of movement. Then comes the detail that makes this project genuinely extraordinary. Construction of permanent infrastructure began on sections of the island before adjacent sections had finished settling. Engineers were building on ground that was still becoming stable, calibrating foundation designs in real time against live settlement data streaming in from sensors across the entire island. There was no precedent for doing this at this scale. Every decision was being made on data that didn't exist until the project created it. China didn't find a location for an airport. It manufactured the ground, stabilized it while building on top of it, and handed the world a fully operational international hub sitting on land that was ocean floor a generation ago. And if creating land from the sea to build a single airport sounds like the ceiling of human ambition, the final project on this list makes every other entry feel like a rehearsal. China's high-speed rail network. Everything you have heard in this video represents a singular act of engineering. One dam, one bridge, one telescope, one tower, each one defined by a specific location and a finite challenge solved once. What China built with its high-speed rail network is something in a completely different category. It is all of those challenges solved simultaneously across an entire continent in less than 2 decades. China's high-speed rail network stretches over 26,000 miles, connects over 500 cities, and carries over 2 billion passengers every single year. You heard that right. One country's train network moves more people annually than every airline on Earth combined. The engineering demanded absolute precision at continental scale. At 250 miles per hour, a track deviation invisible on a conventional railway becomes catastrophic. Every mile required surveying and construction to tolerances tighter than most nations apply to their most critical infrastructure, across seismic zones, floodplains, mountain ranges, and permafrost, often on the same line. But this is where the project separates itself from everything else on this list. At peak expansion, China was completing over 2,000 miles of new high-speed rail every single year. The United States has spent over 15 years attempting to build one high-speed line between Los Angeles and San Francisco. It remains unfinished. China built the equivalent distance roughly every 3 weeks. This is what China's megaprojects ultimately prove. Not that any single structure is the greatest ever built, but that China developed a systemic capacity to take what engineering convention called impossible, execute it at national scale, and repeat that process across an entire civilization without slowing down. The word impossible was never an engineering verdict. China just spent 20 years proving it.